Hello everybody, and welcome to today's webinar that has jointly been organized by Friendship Systems and SimScale. My name is Matthias Brenner, and I will guide you through this webinar on the side of Friendship Systems. My co-host Pavel Sosnovsky will take care of SimScale's side.
Hello.
As you can yes, hello Pavel. As you can see, the title of this webinar is Simulation-Based Design of Complex Geometries using CAESES Free and SimScale. And what this means is that apart from giving you a short introduction into the two systems that are involved here, we will present you a simple workflow that allows you to make use of the free version of CAESES on the one side, as well as the free offering from SimScale as CAE tools in the development process of your products. Of course, we will also demonstrate this workflow on a relevant example, which we will also make available to you for your own exercises afterwards, but more about that later. So one final note before we get started with the content of the webinar. We will not have a dedicated Q&A session at the end of this webinar. You are, however, welcome to post any questions that you have in the GoToWebinar chat, and we will follow up afterwards. Also, you will have the opportunity to post questions later on in our respective forums. So, let me now introduce ourselves a bit more. My co-host Pavel holds the position of Customer Success Manager at SimScale. He has a PhD in environmental and industrial fluid mechanics and is specialized on conjugated heat transfer problems with evaporation and condensation. Myself, I'm currently head of sales for Europe at Friendship Systems. I've been with the company for about 8 years now, previously working in the pre-sales and engineering team here. My original technical background is in naval architecture, but by now, over the years that I've been here at Friendship Systems, I've worked on geometry parametrization and optimization problems in many different fields. So what's on the agenda for today? As I mentioned, we will first give you a short presentation of our companies, Friendship Systems, what we do, and what our software product CAESES is about. And SimScale will also present what they do and the platform that they offer for CAE. After that, I will present the case, the example case that we are going to be looking at today, and start with how we design the geometry for this case in CAESES. And then SimScale will show how to simulate this geometry on the SimScale platform. Based on the first results that we get for the geometry, we will see what kind of engineering decisions we can make and look at some geometry variation. And finally, we will wrap up everything. So let me get started with the Friendship System side. As I mentioned, we are a software developer that is located in Potsdam in Germany. And we produce a software that is called CAESES. CAESES is a so-called Upfront CAE system, which means it's a CAE platform that is intended for this so-called simulation-driven design of any type of shape that is complex and exposed to a flow. CAESES is meant to serve as a platform to run design explorations and formal optimization. And we try to offer all the necessary tools for doing that and the functionality, everything within a highly automated process and in a single integrated user interface. The benefits that one can achieve through using CAESES obviously is that the geometries that one is working on are improved in terms of performance. But also you can explore new concepts or custom tailor your product to a very specific application. And a very important point is that by running these kinds of geometry variations and analyzing the different geometry variants, we can get a very good insight into how the product behaves when we change parameters that describe this product. In terms of the process, the advantages are that we can increase the throughput of the design process and shorten the design times. And another important point is the who's using CAESES, and typically CAESES is used by simulation engineers rather than by CAD engineers, and it allows the simulation engineers to provide their own geometries and also to be able to vary these geometries by themselves without having to rely on a CAD department. This next slide shows in a short overview the components or parts that make up CAESES. So probably the most important component that is also going to be in the focus of today's webinar is the CAD modeling. So we have a very specialized CAD modeling to provide simulation-ready geometries and being able to vary these geometries in a very efficient way. Then in terms of the process workflow, the next component is the interface to external simulation software. So we don't have our own simulation softwares. Otherwise, it wouldn't also make sense to collaborate with SimScale. But we hook up to all kinds of simulation softwares that are available on the market. And finally, the last component that is part of CAESES is the optimization part, so that you can drive the whole design process in an automated way to run design explorations and formal optimizations. Since this webinar is focused on CAESES Free, and so the users of our free version, let me just highlight here what is included in the free version of CAESES. So basically, you can see that most of the parts shown here are also available in CAESES Free. The one thing that is not available is the optimization. So with CAESES Free, you can generate geometries and couple to simulation software, but you will not be able to run automated optimizations or explorations. All right, let's go into these three components a bit more. So as I said, the most important one on our side and also for this webinar is the Upfront CAD component. So we are specialized on creating geometry for analysis. So we're a little bit different than, let's say, the traditional CAD tools that have obviously a very wide range of functionality. We focus on, say, a small niche of that to provide the geometry that is necessary to run the analysis or simulations that you want to do, and especially being able to change the geometry that you're working on in a very easy and efficient and also robust way. We have different strategies that can be used within CAESES to create a variable geometry model. The first one we call fully parametric modeling. This means that the geometry model is built from scratch completely in CAESES, and obviously this allows a very complete control on the geometry and also very detailed control. There is an example here on the side for a fully parametric model and how it's being changed. The disadvantage about the fully parametric modeling approach is that obviously you have to invest a bit more time to generate your parametric model, while with the second approach, the so-called partially parametric modeling, this is very fast to set up. So the approach here is that we import an existing geometry and then apply some kind of morphing and deformation. As I said, it takes a little time to set up, but as a disadvantage compared to the fully parametric modeling, we don't have such a detailed and exact control on the geometry. Yeah, two further things to, let's say, point out about the modeling approach in CAESES is that our goal is to get to a very efficient parametrization of the geometry, so we are working with complex geometries that are traditionally in other CAD tools not so easy to parameterize, and we want to describe them in a parametric way so that they are very flexible, but also that they are described with as few parameters as possible, because this will save time in later optimization studies and such. Another important aspect when you're changing geometries and optimizing geometry is that you have to take care of constraints on the geometry for different reasons, functional constraints or manufacturing constraints. And we can obviously monitor constraints in CAESES on the geometry, but also, which makes it more efficient, we can also build these constraints directly into the model so that all the designs that are being created fulfill these constraints automatically, and during your variation process you only have feasible designs. So let me now quickly speak about the final two components of the typical CAESES workflow. The coupling to CFD is the next one. CFD, or actually I've written CFD here, but it can also be other kinds of simulation tools, as we will see in our next webinar next week. So CAESES can connect to any simulation tool that can be run in batch mode, and when you have set up this connection, then you can very easily start the analysis or even a fully automated workflow to run a design variation with just a single mouse click. The external software will be controlled by scripts so that you can also involve solver or mesh parameters into your design study apart from the geometry parameters. And obviously there is certain things that are critical, like robust automated meshing so that you're able to automate the process. In today's webinar and the workflow that we will be showing today, we will show a bit more of a manual process. So we will focus on the geometry creation, and then we will also say manually move the geometry to SimScale to run it there. But let me say already as a side note now that we are working on a more tight integration to SimScale, so that the plan is in the future that you can run your computations on the SimScale platform directly from CAESES, and the geometry will be transferred automatically as well as the results. Yeah, the final step of the process is the optimization part. So we have a couple of built-in design of experiments and optimization algorithms in CAESES. Additionally to that, we also have a custom integration and an interface to the Dakota optimization toolkit, which is an open source, very state-of-the-art optimization toolkit. And after you have run the optimization, you create a large amount of data. So we have tools for automated reporting and analytics on the results, as well as assessment of the optimization studies with charts and plots and so on. We also have some additional tools like our resource manager, so that you can distribute computations to remote machines if you are not running everything locally. So finally, to give you an idea of the typical applications of CAESES, as I mentioned, we mainly deal with geometries that are complex in shape, more difficult to parameterize, and exposed to flow. So for example, we have ship and boat hulls. This is the industry where we originally come from. And then there is other applications like powertrain components, as we see here, the intake port, or turbochargers, propellers, valves, fans, or turbines, all kinds of shapes like that. So much from my side as an introduction into friendship systems and CAESES, and now I would like to pass over to Pavel, which will give you an introduction into SimScale and the platform.
All right, thank you, Mattia, for this brilliant introduction to CAESES, and I'll move on to a word or two about SimScale and the new approach to computer-aided engineering that we are bringing to the community around the world. But before we do that, let's take a look at the way that simulations and product design process has been over the years before we introduced the computer-aided engineering. In principle, we were forced to build a physical prototype after we had prepared a design, and then with this physical prototype, we performed the testing, made the redesign, and finally were able to build the product and release it to the market. The whole process was pretty costly and time-consuming. Thanks to tools like CAESES and SimScale, we were able to shorten the process and even, in some situations, remove the requirement of building a physical prototype so that the optimization of the design can be done fully with virtual tools that are created and available. This obviously grants us the possibility of saving money and releasing the product faster, and in some cases even more reliable, since it's not that cheap to build 20 different prototypes of a wind turbine. What SimScale brings to the market is the challenge to the three barriers that so far were blocking most of the people from using CAE tools for their product design. First of all, we are accessible. You do not need to install anything on your computer. Even better, you don't have to have a powerful computer. Everything is running in the cloud so that your calculation can be performed using a tablet, or a PC that does not have huge capabilities. Further, we're really cost efficient. With a subscription-based model, you are able to run your simulations at the very beginning for free. And later, when you're ready to get for a professional account and you would like to get some privacy, you have the possibility of going for a plan that brings it to a reasonable price. And finally, this is for everyone. One of the biggest challenges for any CAE engineer or person who starts is the amount of knowledge you need to have in order to perform any kind of simulation. We combat that by creating a community of engineers who share their experience and expertise, providing public projects for everyone to use, learn, and start from. So what is it that we give you? A full simulation capability, from basically a full range of fluid flow simulation, incompressible, compressible, steady, laminar, turbulent, supersonic, you just name it, with support for different technologies, rotating zones, porous media, potential flow, particle flows, and so on, enabling the use of state-of-the-art solvers for fluid flow simulations. Further, we take a step more. Now, with the same package, you get immediate access to structural mechanics with static, dynamic, frequency, bulking. You just name it. But that's not it. You go with particle analysis, multi-physics problems like conjugated heat transfer problems or thermomechanical optimizations. With rotating zones, different capabilities, and solvers that allow you to make advanced simulations in your web browser. That would be a very short introduction to what is it that we are doing, and I will be talking a little more about the platform itself and the capabilities when we jump to the live presentation. But for the moment, I will give the mic once more to Mattia, who will introduce the case that we will be using as an example, and he will guide us through the preparation of the CAD, so the first step before we jump to the simulation part. And I'll take the mic back to talk more about the simulations.
All right, thanks Pavel. So what is the case that we're going to be looking at today? As you can see in the pictures, and there were some pictures or pictures already in the introduction, the topic for today will be working on an axial cooling fan So this is a 6-bladed fan. As you can see in the picture, the diameter is 100 millimeters. So this is basically similar to your typical cooling fan that you would have in your PC case to cool the CPU or something like that. And obviously we want to look at certain design targets for this fan that we will run the simulations for. And typically for a fan like that, you would like to get as much of or as high as an airflow as possible, which is measured, say, for example, in cubic meters per hour or cubic feet per minute. And obviously, if you have more airflow passing by your cooling device, you will get a better cooling. That's the one thing. The other target, which is partially, let's say, conflicting with the first target, so we will see how this goes, is that we want to keep the torque that is applied on the axis of the fan for the rotation of the fan as low as possible, so that we can use a smaller electric motor, or in general consume less energy when driving the fan at a specified RPM. So let's take a look now on my side how the fan is modeled in CAESES. And as a first, let's say, theoretical introduction, I would like to introduce the concept of the Metasurface, which is our own development here in CAESES, and it's a, let's say, a special surface type that allows what I mentioned before to parameterize complex surfaces, free-form surfaces in an efficient way. So the generation of a metasurface starts with a curve definition that we see here in the bottom in the first step of the diagram. So let's say we want to model a wing or the fan blade in our case. We start by defining a profile section, and this curve or section of the surface is described by parameters. For example, as you can see here, the chord length. Now, as a next step, these parameters in the direction of the surface, so for a wing it would be, let's say, the span-wise direction, or for our fan blade it's the radial direction. In this direction, the values of the cross-section parameters will change. So we can, in the next step, we can set up functions that describe how these parameters change. So for example here, our chord length from the root of the wing to the tip is decreasing. And finally, in the last step, we connect these two information, the cross-section definition with its parameters and the description of how the parameters change. And with this information, we are able to generate a smooth surface. So to say, we are doing a continuous lofting of our cross-section, changing the parameters so that we get the surface. So how does it look like for our fan blade? Here in I'm showing the first step of the process. We just saw our cross-section definition. So in our case, we have a profile definition, a rather simple one with a couple of parameters that you can see here in the picture. We have, for example, parameters that control the camber line of this profile, like the chord length and the leading edge angle. This is this alpha parameter. And the trailing edge angle, this is the beta parameter. Furthermore, we have parameters that control the thickness distribution along the profile. So we have the radii at the leading edge and at the trailing edge. And we have the spread angle or wedge angle. It's also sometimes called, that describe the shape of the profile between the leading edge radius and the trailing edge radius. Finally, we have some positioning parameters for our profile. So the first one, which is illustrated here, is the pitch angle. So we can obviously rotate the profile about the leading edge. And we have two other positioning parameters, the circumferential position to move it around the cylinder at the specified radius, and the axial position to move the profile in axial direction. Okay, so this is our cross-section definition with all the corresponding parameters. And now, as I mentioned before, we set up some distribution functions that describe how these parameters change in the radial direction of our fan. So we can see here in the picture the values of the different parameters plotted over the radial position. For example, here this is the chord, which from the hub to the tip increases, or the pitch is decreasing, and so on. And the shape of these distribution functions or curves is controlled by individual parameters. So for example, we can control the start and end value of the curve, or the position of the control points if the curve is modeled using control points like we see here. Alternatively, we could also specify things like the tangent at the start of the curve or at the end, or if the curve has a maximum or minimum in the middle, we can specify the value and the position of this maximum or minimum, or we specify the area, so the integral below the curve. So many different types of parameters that can be used to describe the shape of these distribution functions, and by controlling the distribution functions, we will finally have an effect on the surface. So if we want to modify our surface, we modify the parameters of these functions. Yeah, and the last step of the generation of the blade surface is the generation of the actual metasurface, which is based on our parametric profile definition and the radial functions. This is a smooth NURB surface, and it's just the surface of the blade, so it's open at both ends. So in the next step, we have to intersect our blade surface with the hub and the shroud. This will close the blade tip for one, and it will also merge the blade with the hub here in the middle. The hub geometry is also parametric, so you can change diameter, the radius of this edge here in the front, the height of the hub, and so on. And the shroud is simply controlled by one parameter. This is the diameter, the total diameter of the fan. Yeah, in the next step, we add the fillet at the root of the blade, so between the hub and the blade surface, with a specified radius that can be controlled, and we basically repeat the same process for the specified number of blades that we want to use. And this will give us the final model, and then we could go in and vary our geometry in a manual or in an automated way, as you can see here in the animation. To prepare for the computation, finally, we modeled a further cylindrical zone around the propeller. This will specify the rotating volume later in the CFD setup. So Pavel will show how that is used. And then we select the propeller and the cylinder and export everything together in a step file. We also have other alternatives that maybe in this case are not suited, but in other geometry examples, when you transfer the geometry to the CFD setup, a very suitable format is also the so-called multi-body STL export. So this is a tessellated format, but the good thing here is that it allows to transfer named patches for the grid generation so that you can address certain parts of the geometry in your grid generator by name, which makes it easier to automate things. Okay, so much as a theoretical introduction. Let's change over to the CAESES user interface and take a look at how the model looks like. So this is the CAESES user interface. I see that make things a bit bigger so you can read everything. And so we see here the user interface. On the right side we have a 3D window where you can see the 3D geometry. You can rotate things and select things, obviously. On the very left we have the so-called object tree. This will show the complete object structure of your project, so you find all the different components and parameters of your project in this tree. It looks very much like a folder structure, let's say, on your Windows computer, for example. And finally, if we select an object here in the object tree, you will see that in the middle we have this further window, the object editor, where you can edit the properties of this object. So I mentioned already a little bit this tree structure. So this project is also structured in a, let's say, more or less clean way using these folders. We call the folders scopes, by the way, in CAESES. And here in the structure you can find the different components of the model. So we have the shroud, for example, and the hub geometry. Then we have a folder with all the radial functions that describe how our parameters change in radial directions. We have the generation of the blade and of the final fan geometry, and then some additional folders for the rotation region, and also a, let's say, optional STL setup in case you would want to export the geometry as STL. There is some settings included here. So I opened a couple of these scopes or folders, and you can see already there are some parameters here that can be addressed. For example, we have the radius of the shroud, so this controls the overall diameter of our propeller. We have some parameters here for the hub and things that control the blade shape, like the leading and trailing edge radius. These are fixed values in radial direction, so we don't have a function, but they stay fixed over the complete radii. So let's take a look at our functions. Let me hide the fan now. So maybe here as a note, if you click onto these folders or on other objects, on the icons, you can make things visible and invisible. So now I'm making the final fan invisible and visualizing the functions. Let's open up another window where we see our functions, the ones that you also saw just now in the presentation. And if I now visualize the blade surface that has been created, and maybe not the shroud but the hub in the middle, we can take a look at what happens. So if we go onto our parameters here, we can change, for example, the diameter or the radius of the fan. Let's say we change it to 60, and then everything is updated accordingly. Other parameters, like we see here, the radius of the hub, for example, is set as a relative value to the main diameter of the fan, so that if we change the overall dimension, everything will scale accordingly in a nice way. And if we go into a bit more detail, let's say we would like to modify our chord distribution, so this function here, we find this curve here in the corresponding folder, and now we go, for example, in the endpoint of this curve, and we can change the value here, increase the chord at the tip of the blade, and you probably saw in the 3D view that the shape of the blade changed. Let me do it again. And so on. So, so this you can do at every, let's say, position in the geometry. Either you have a parameter already as the ones that you can find here in the project, or you have to go into the geometry somewhere. You can also create new parameters at a certain point, and now you have the possibility of addressing, see the, for example, the tip chord, oops, directly. Okay, this is just a small introduction into the model and how you can change things in this model. We will come back to that when we're doing some design changes. Just let me finally show you here. This is the rotation region that we created for the computation, and in order to make the step to the CFD setup, we need the final fan geometry and the rotation region. You can select these two things, and then you would go in the File menu, Export, Step, export everything in the step format, and then you are ready to set up your computation on the SimScale platform. And that's also the next step in our webinar, and I will give back the word to my co-host Pavel now.
Okay, thank you, Mattia. Let me just switch the screen, and we will show and go to start the simulation with SimScale. The first thing to do will be to decide how shall the domain look like. Even before we jump and prepare the idea or prepare the analysis, we need to understand the physics that we're going to simulate and try to reproduce it for every variant of the simulation. In this particular case, we'll decide to create a certain open box where the fan will be rotating inside. We'll set one of the faces to be the inlet. The fan will be rotating when you look at this counterclockwise, and the other face will be the outlet. And we'll be directly importing the CAD design that was created in CAESES to SimScale platform using the step format that is being supported. In order to do that, I'll jump directly to the platform itself and show you what is it that you see whenever you log into SimScale. First of all, what you'll notice is the dashboard of all the projects that you are working on. And most of your projects, if you go with the community plan, will not be marked with the little lock. This means that they are publicly available and ready to be used for other users in the public domain. You have hundreds of projects with different simulation types ready to be viewed, copied, and used as a starting point for your own analysis whenever you want to make any simulations. I'll just go back to the dashboard and jump to the project of the fan analysis that was prepared here. So with the dashboard, we have a short overview of the geometry that is available and a little actions that you can perform. The great thing about SimScale is the possibility of sharing your knowledge. If you would like to invite people to the project, it's as easy as putting their emails over here, giving them a message, and they will be invited to get a copy of your work. You can also find it, do some standard things like editing project properties or making copies for later use. But most importantly, we'll go and open the workspace that is the heart of the simulation designer. Over here, you will get the 3 steps of simulation that need to be performed in order to make an analysis like this. The first, pre-processing or meshing, the simulation designer, and the post-processor. These are available on the top of the menu bar. I will start with the baseline geometry that we uploaded. You will immediately see that we prepared a little more variants, and in a moment Mattia will present on how to create those in CAESES. Let me just hide the geometry. We have uploaded it directly using the upload mesh button, upload geometry, and selecting the step file, choosing the file. Very easy. Now we're ready to mesh the geometry. We can start just by right-clicking on the name and creating a new mesh. There are 2 ways of generating a mesh on SimScale with 2 different types of meshing. The first type of mesh is the tetrahedral mesh that is mostly used for structural analysis or some very complex flow simulations. The second one is the hex-dominant mesh that is applicable for CFD. And in fact, for rotating zone simulations, we will be choosing a parametric approach that is more advanced, has quite a lot of parameters and information to be used in order to create a mesh like this. On the other hand, you are never left alone. That's why you have the public projects to give you an advice on how to approach a problem like this. Also, forum topics and community users who will be more than happy to help you with the analysis itself. But if you are not dealing with a rotating zone simulation, you would like to see a flow around the boat shape or any kind of other analysis, you can go with the automatic approach, which speeds up and makes your life much, much easier. Notice that there's just one parameter that really needs to be set. That is the choice of how fine do you want your mesh to be. And for external flow simulations like this one, we would also have to decide the size of the box. That is defining the place where the fluid will be moving. This time we went for a hex-dominant meshing, so we'll have to do a little more of work. The mesher will automatically create the bounding box after we click save, but then this is definitely too small, so we would have to set it up in order to create a domain that is sufficient for the analysis of a fan like this. I will not use too much time on doing that since it's already been prepared. But the great thing with the approach is that you have full control over the mesh quality, different types of refinements such as region refinements, surface refinements, feature refinements, layers, you just name it. It's all available within one package. And in the end, you'll be able to obtain a mesh that looks something like this. Let's just give it a second to load. So there we are, a box that defines the fluid flow zone. I'll just hide some of the faces. We see the rotation zone that has been meshed, and if I hide it, we'll also notice the meshing that has been done around the fan itself. We also define some meshing regions. If we make a cut through the mesh, after a second, we will see the refinement zone behind the fan that will allow us to properly resolve the wake of the flow. Interesting fact about this whole platform is that it is running in my web browser. I have not installed anything. I have not downloaded anything. I just opened the Chrome web browser, logged to SimScale, and I'm ready to make all this analysis and create the meshes. Even more, no meshing is done on your local computer. When the operation begins, you can simply log out, switch off, and travel to another country, log back in, and find out that your result has been created, like the mesh over here. A very nice structured mesh for the simulation. From this moment on, we're ready to move for the next step of the simulation process. We go to the Simulation Designer on the top menu bar, and for an example, I'll create a new simulation where the first thing that I'll have to do is decide on what type of analysis do I want to do. A few minutes ago, I gave you a brief description of what can be done with SimScale, and there is quite a lot. From solid mechanics analysis, like static analysis, stress distribution analysis, to dynamic problems such as drop tests, deformations, or bulking elements, to model analysis, which we'll discuss next time, and frequency or harmonic analysis. We go next to fluid dynamics, incompressible, compressible, natural convective heat transfer, and now a new feature that is the conjugated heat transfer, in which not only do you see the buoyancy effects created in the fluid domain, but also at the same time you simulate the heat transfer within the solid domain. You can have a full simulation of a heat exchanger with 2, 3 fluids separated by a pipe of a certain thickness, all modeled at once with the proper behavior of the thermal analysis at hand. The passive scalar transportation, very important to notice the tracking of certain distributions. For example, some dyes that are imported to see the flow patterns or recirculation regions that are not flushed away with the new flow. Multi-phase flow simulations, where we have the non-mixing fluids interacting with each other. Interesting addition to that is the 6 degree of freedom simulations, where you can have the boat float on, or any kind of object, float on the surface of one fluid being submerged with the buoyancy and Archimedes' law. Some discrete phase models. You would like to see how would the particles behave when you put them in a fan or your turbine. Where would they go and how would they move? Or a cyclone separator, if the particles are behaving in a proper way. It is there just for you. I already mentioned the solid mechanics, but then we go to thermomechanical and thermostructural analysis, which also is a pretty important element where you simulate the response, the contraction or expansion of metals or other materials due to the changes in the temperature of the geometry. And some heat transfer analysis. It would seem a simple thing just to model a thermal behavior of any kind of an object. But then, starting with a small thing, what I like to call a low-hanging fruit approach, may gain you a lot of time when it comes to trying to struggle with a super advanced simulation, which results not always correspond to what you really need. We have also acoustic simulations, particle simulations. This is just a discrete phase that is being dropped from one place to another. And all this is available for you from the very beginning that you log to SimScale platform. Now, let's go and check an incompressible simulation and press start to confirm our choice. Now, 2 things will happen when I do that. First of all, you will notice the little saved changes in the bottom right corner, which means that all the work that you've done till the moment you pressed save is being transferred to the servers and is secure. A lightning may strike your computer and your data is stored and you can go back and work with it anywhere on Earth where you have internet connection. The second thing that appeared is the tree on the left side. And you will notice that this structure of a workspace is very similar to what we have with our friendship systems and in CAESES. You have the tree view and and the properties panel in the middle with the viewer on the left side, on the right side. Now your job in order to prepare the simulation will be to go from top to the bottom of this tree, selecting the parameters and deciding on what kind of elements are required for your simulation to work. We'll go choose the domain, we'll select the material, we'll choose the boundary conditions, and even collect data on the surface of the fan in order to be able to gather the forces and moments. Oh, in this case I'll have to delete this. It was not the surface, but forces and moments, in order to directly calculate the moments acting on the fan blades and have the results ready. When the simulation is set, we are ready to prepare one of them and set it to run. In the simulation control, you can not only choose the duration of your simulation, but most importantly, how big of a supercomputer machine do you want to use for your analysis. And you can have any number of simulations running at the same time with any number of computational cores assigned to them. So I can, like last night I was running 6 simulations on 32 cores, no problem. Nothing is running on your machine. And as they are going, you can monitor their progress, see the residuals, and decide on what to do with them. When you have the results ready, you can do 2 things. Either you can download them and use offline post-processing tools, maybe import it to CAESES, or use the online post-processing provided by SimScale. Everything done, once more, in a web browser. For this case, we could visualize the flow and create some nice imaging plots. Since we are getting short on time, I will not be doing that. I'll just show you the very beginning, what happens after you load the thing. And in fact, this box that appeared here is in fact, how would I call it, an interactive image visible in your web browser. So everything is streamed, nothing is even rendered on your computer. And in the end, with the use of this tool, you can create images like this ones with nice opaque visualizations of the velocity magnitude. Further, we already gathered some information in the force plots so that we could see what kind of forces are acting on our fan as it is moving through the air. In this case, I'll just hide the pressure moment, the pressure force in the z direction. Of course, there is a drag, but then we can also investigate what is the pressure moment in the z direction, take a note, and later compare it with the second type of designs that Mattia will now introduce to you.
All right, thanks. So we've seen a little bit of the setup, how to prepare the baseline computation, and now I would like to show the following steps. So let's assume we have now computed the baseline and we have received the results that we're interested in. That is the moment around the z-axis, so that's the torque that the fan will need to spin, and also we got an information of the mass flow, or not mass flow, sorry, the volume flow that this fan is moving, so in cubic meters per second or per hour. And as I said, these are the 2 parameters that we would like to improve our fan on. So what I want to show you now is simply how to create some variants for this fan that we can then again analyze in the SimScale platform. And the 2 variants, or I have some things in mind that we could do, let's say very simple changes based on airfoil theory. So if we want to increase the flow that is induced by the fan, basically we would like the fan blades to create more lift. So the two things that easily come into mind are we can increase the angle of attack of the profiles. So for the fan blade, this would mean increasing the pitch. That's the one thing. And another thing that comes to my mind is that we can increase the camber of the profile, of the blade profile, so that we can also generate more lift or more flow from the fan. So these are the ideas that I have in mind. So let me show you now how to create these variants. So I'm back in my CAESES user interface. I'm currently in my baseline design, the one that we started with and that we computed as the first one in SimScale. And now I would like to create a new variant, so I can go in the optimization menu and say create a new design based on the current design. So now I have a new design here. You see here are already the variants that I created previously. And now we are not working in the baseline anymore, but we have basically created a copy of the baseline that we can now modify to as we want. And as I said, as a first thing that I would like to change is the pitch of the blade. So I'm not going to change the pitch of the complete blade, but let's say I want to keep it constant at the root, because at the root of the blade we already have quite a big pitch, so maybe much more would not be good because we might get flow separation or something like that. So let me go into my functions, and now in the pitch function, and the first point here describes the value at the hub, so at the root of the blade. And now I just want to keep that fixed and just modify the other ones. So let's say for the middle point at the midspan of the blade, I increase a little bit, and at the tip of the blade I also increase the pitch a little bit. Maybe you saw it in the 3D view. And now we have our first variant with a higher pitch at the tip of the blade. And I would go back to my baseline, create a further variant based on the baseline, and here I would like to change the camber of my profile, and the camber I would like to change for the complete blade, so not only at the tip. So the profile parameterization I showed you before does not have a camber value directly that we can change, but I'm going in my setup of the Metasurface where I can control all the parameters. And here for the camber, you see I have these two angles, alpha and beta, that you might remember control the angle of our profile at the leading and at the trailing edge. And by increasing these values, I can increase the camber. So let's say I change this to -15 and this one to 12.5. Then since these are constant values, so not controlled by functions, these will change the camber throughout the complete span of the blade. I have two slides here just because it's a bit difficult to see in the 3D model these changes. They're not very pronounced, but here I have the just one section of the blade at the tip, and so here you can see how the pitch increases for this section. And another animation here shows you how the camber increases. So this is original and this is changed. Okay, so now we have our variants. Like I showed for the baseline before, we can again export them as step files and then go back in the SimScale platform, run the computation for these designs and compare the results to the baseline. So Pavel will now show the results.
As Matthias said, we created 3 variants of our designs, and now I would say how would I create the simulations for them and how hard can it be. So in fact, once you created your first mesh and your first design, modifying it and using a different variant is very simple. You will first right-click in your mesh creator and duplicate the existing mesh. After a second, it will appear in the viewer. We'll be ready to delete the results of the copy and simply substitute the geometry with the second one. Of course, all the assignments will go away, so we'll have to decide where do we want the layers to be selected, where the surfaces are gone, but as you can see, it will take me just a second in order to make this kind of assignment. So I'll just select everything, add selection from the viewer, the same with the assigning the surface refinements and the rotating zone. And we're ready to go. We just need to press start in order to recalculate the mesh. And a similar procedure can be obtained in order to create another variant simulation of your baseline profile. I could just duplicate the simulation, substitute the mesh, and reassign the inlet-outlet material simulations in order to obtain variable results like this one and be ready to run them immediately and further post-process them in the online or offline post-processing tools. So I'll just jump back and show you the results that we obtained over here. First, we calculated the amount of the pushed flow in cubic meters per second, and with the baseline giving 8.8 or 8.9 10 to minus 3 cubic meters per second, we see that variant 1 performs the best when it comes to the amount of air that is being pushed. At the same time, it requires a little more moment. There is more moment acting in the z direction on this geometry. So if we were to increase the amount of flow that goes through the blade based on the baseline, but we would like to keep the power consumption low, that's where the variant number 2 would shine. The decision on what kind of choice would you make comes to the designer himself, and you can go and optimize based on different parameters and different goals, the targets that you want to achieve. The great thing is that the process is, even though it's manual, is very fast and easy to be performed both with CAESES and with SimScale. So we are a little over time, but I would like to invite you right now to take your hands, to take and have a first-hand experience of using both CAESES and SimScale. We prepared for you special forum topics where you can first download the geometry and download the project with the fan design that Mattia presented in CAESES, and later visit SimScale's forum topic with a description of the workflow required in order to create a simulation. Take your chance and make your own simulation trying to improve the design based on the parameters that you think are most important for that. And later, send it back to me or to Mattia so that we can evaluate and see and answer any questions that you would have when it comes to this kind of workflows. All right. For now, I would like to thank you for joining this joint webinar from Friendship Systems and SimScale. We will have the next session coming up next week at the same time. If you would like to ask any questions, feel free to go to ask us directly or go to the forums that I mentioned earlier. And yeah, have a great evening, and thank you very much for attendance.
Thank you also. Bye-bye.
Have a great day. Bye-bye.